short-term demand forecasting. Second, review of basic curve fitting. Most of the early applications of forecasting included curve fitting of some sort. The curve fitting could have been as simple as linear regression, exponential filtering, assuming that the signal was of exponential form, or double exponential, and therefore double exponential smoothing was used. Time series, as we are looking into them, we assume that demand is assumed to be a reoccurring pattern. So the base demand is constant, and there is an annual growth with it, a trend. There are seasonal patterns, heating, cooling, day of week in terms of the work week, and some econometric inclusion. In essence, what do we do with our income? Discretionary income in particular, but also non-discretionary when it comes to basic items. Purchases are normally driven by some kind of budget excess, some extra cash that we have. Once our basic needs are filled to our desired level, we then acquire other goods for use. Manufacturing, such as steel mills or food production, meet the expected demands by knowing what to produce the forecast is. The time series model, as we said, will be separated into components as a decomposition into a base, a weekly, a seasonal, which could be quarterly as per season of the year, after which it is named, weekly because of the weekend repetition from one weekend to another, and also daily. Of course, at the very end, we will have noise, which we assume will be negligible or totally unpredictable, and therefore we cannot do any better. Okay, what are the short-term factors? Well, hour of the day for a specific day of the work week. Most people work 8 to 5 or 9 to 5. We have weather influences that change the temperature, wind speed, wind direction, humidity, cloud cover, sunlight, etc., and therefore our use of energy for heating and cooling. There's hour of the day pricing strategies, which change the use based upon price incentive. There are special events, social for the most part, like strikes, special TV programs, major political events, a convention, etc., or an election that will change demand use. The amount of distributed generation, especially solar cells, biofuel, and natural gas microturbines, and very possibly smaller wind generation in the future will change the demand profile rather strongly as people wish to be more green and therefore use less environmentally dangerous resources. The amount of demand response seems to be changing with transactive energy. This used to be called demand side management. Penetration to shift demand from one hour to the next or from the on-peak period to the off-peak period. Economic conditions. The more money we have because our wages are going up means we have more money to spend, especially on things that we normally don't spend, such as energy use. Random unknown factors are treated as noise with minimal impact. Basically, there's nothing we can do about them. The quality of fit can be measured by many statistical measures. The mean error is very common. The error deviation of this is very standard. We can also look at the harder moments like skew and kurtosis. Mean square error, mean absolute error are very good indications of the quality of fit as the curve deviates from the actual curve, and many others as we will define in future applications. The error metrics, the error is just the difference between the actual signal and the estimated signal, or in our case, the estimated demand and the actual demand. The absolute error is one way of measuring the amount of inequality in fit. The MAD or mean absolute deviation gives us more of a statistical term to look at the difference between the actual and the forecasted demand, weighted by the number of samples, as well as the mean square error. Note that both the absolute value and the square of the error change any negative value to a positive value, and equally weights errors above as well as below the actual value. Hourly system demand forecasts are the most common thing to be done. We look at the next 72 to 168 to even 336 hours, and even just to tomorrow for doing a daily bid on the energy markets for tomorrow. We separate the base demand from the actual demand and look at the remnant, which we assume is some form of the previous changing demand and the noise. So system identification is the first process. We decompose. We have to separate things into components either additively or multiplicatively. We have to know the order of the equations, that is the number of terms, how many parameters are involved. In state space, we worry about the shape of the A matrix. Our ARMA, is a row of state variables with a diagonal component, a very simple A matrix. And we can also look at other feedback connections to take care of econometrics and also to shifting of demand based upon storage and upon use changes as prices entice people to change their behavior. There are outliers, those events which we really cannot forecast because they happen very seldom, and therefore history is not repeating itself. Tiny Tim getting married on TV was one of those that almost blacked out New York City because the older generation did not understand Tiny Tim as a pop fad. And when he got married on the Tonight Show, the electric demand was at an all-time high for people having parties to watch this event. We now have distributed supplies such as solar PV cells that are changing the demand on a per residence or per building basis. Demand response is allowing people to be price sensitive. That is, they can take their energy when they can best fit it into their budget. They may demand shift. That is, we might use a heat pump with thermal storage to shift the heating and cooling needs from the peak period to the off-peak. And we can also do production time shifts, as happened in California when the electric price of energy skyrocketed and companies moved their production hours to the off-peak periods, the evening period and overnight. Also, the other thing we need to consider is the ancillary services, such as frequency and voltage control, as part of the forecasting problem. Environmental control is the only econometric model we'll really get into to show how time series can absorb some of the economic impact of changes. Environmental in this case in terms of the temperature outside. This is a bathtub curve as shown in the book during rather nice days when the weather is temperate. Very little air conditioning and heating is used. As the summer heat gets to all of us, we turn on more of our air conditioners. And as the winter cold gets to us, we turn on our furnaces. And that is what's represented in these three equations from the text. The weather model can also be written as a state estimation formulation and solution as shown in the following. This is identical to the one in the text, where we have the demand as some matrix H, that is the change in temperature over time, times the state plus some noise. And of course, we can use the state estimator approach to determine those parameters. An alternative formula to do the same thing in terms of econometrics is to look at period differenced polynomials for summer demands and winter demands, and add saturation in for those periods of continuous heating or cooling when all of the devices are on. So until all devices are on, we have what we assume to be a random occurrence of devices turning on and off during the hour. And as the heat continues, that will increase and we will get more continuous use of appliances until we get saturation of the need for the heating or cooling. So our time series is going to be some basis, a trend, some seasonality, periods represented over some time, daily, weekly, or seasonally, and the remainder is going to be random, and we're going to assume Gaussian for this course. And so what we want to be able to do is to identify each of those components. The least squares curve fit is the most common technique used. Many of you have learned this technique in a beginning engineering course, where you would take data and fit a line to it or a polynomial. But given n pairs of data, you're to find the coefficients of alpha and beta such that the function f of x will fit that data. So it's a good statistical fit to the data. So you look at the difference between the actual reading and the predicted reading by the parameters of alpha and beta. Common solution to this is with an overdetermined system of equations. You set the derivatives of the objective to 0 to find the optimum value. And if you notice here, we have the same equation we had with the state estimator of A transpose A and A transpose B. And indeed, we could use the same software. So for an example, this is a example out of a book on numerical methods with Matlab, implementation and applications by Rechtenwald in 2007, an excellent book for learning Matlab in terms of the things we're doing in this chapter, but shows that as we have the actual data, the dots, we fit a line to it, and the line magically, because it's the optimum, goes in between the various samples. We can also consider, instead of a square fit, we use a square fit because that is the most easy to compute the derivative. We can also use an orthogonal distance fit, which is an alternative to minimizing residual, so we minimize the orthogonal distance to the line. This is known as orthogonal distance regression, and the reference by numerical methods with Matlab by Rechtenwald is a place to see where it's replicated. The original work, as referenced in that book, is from Numerical Methods for Least Squares Problems back in '96 by Bjork. One way of measuring the quality fit is to look at the R-squared statistic. R-squared can be applied to linear combinations of basis functions. R-squared is a measure of how well the fit function follows the trend in the data. And R-squared will be a value between 0 and 1. Recall that for a line fit, where headed y is the value of the fit function evaluated at each x, and y bar is the average of the known y values for a linear combination of basis functions. We have that the estimate is equal to the sum of the coefficients times the basis functions. So if r squared is equal to 1, then the fit function follows the trend of the data. If r squared equals 0, then we don't have an answer statistically better or significantly better than approximating the data by its mean. And this is the math equation of the r squared statistic. We can use the r squared statistic adjusted based upon the number of samples because of the degrees of freedom reduction in the data. It's technically appropriate to consider this adjusted coefficient determination instead of the original, just as the sampled variance is more appropriate. We can transform the linear functions into other forms and therefore do some nonlinear fit functions. Linear least squares fit to a line is performed on the transform variables. Parameters of nonlinear fit function are obtained by transforming back to the original functions and variables. Linear least squares fit to the transform equations does not yield the same fit coefficients as a direct solution to the nonlinear least squares problem involving the original fit function, but it will be very close. Okay, so it's not that we don't get a good fit, we will not get the same numbers. What are examples of nonlinearity? Well, natural log is one of them, where we take the natural log of each side. And we can also extend this to linear combinations of functions. And this is where the art of the forecasting comes in terms of which functions to use and how to combine them. Other nonlinear functions are the quadratic function, the exponential function, the nth order polynomial, and the c over x plus cx function is another one that's very common in usage. How do we do it? How do we test these? Well, what we have to do is we have to do benchmarking. We have to compare the new technique to an older technique to see which one is doing a better job. We have to statistically analyze accuracy improvements, and the improvements are immediately shown once we look at the various measures of the error, the square of the error, or the r-test. The first thing we should do in testing all algorithms, instead of using real data, is to do a prototype and initial testing where a function generates a known solution where errors are or are not present. So we don't add any noise as the first step. So the first thing we want to do is we want to debug the code. Is what we really want to do. Is we want to be able to go to the prototype and say, yes, it's working. I told it that I gave it the data for a sine function, and it found the same sine function. Therefore, the program is probably working. And if I give it other functions and it finds them, then it's probably working. Now, once I add noise, then we're going to see what the algorithm limits are for accuracy and how far the noise degrades the algorithm is of use when we're investigating new algorithms. Now, data generation, what do? Well, for initial testing, straight line for curve fitting is the obvious thing to try. Quadratic line is the next one. And then sine terms for Fourier analysis is very useful in our work of demand because our demand does follow a sine or cosine set of functions with the peak and troughs each day and weekly patterns, monthly patterns, etc. ARMA is another one from Box and Jenkins, ARMA or ARIMA. We generate an ARMA function with known parameters and generate the time series and see if we can find those terms. If we generate an AR of one term, the program that we're using should find an AR of one equation with the same parameter if it is functioning properly. Only after we add noise can we then see what happens. So we want no noise at first. So we generate a time series of signal with no noise to check the program, check our data collection, check our assumptions, and then we add noise to it to see how well things are working. So we add as success is found. We add more terms as the algorithm works. When we get done with the algorithm we just tried, we look and see what is the pattern that is there. If the algorithm fails, then we don't no longer add that type of algorithm or that kind of functions. We look at what is left. If it's something we can live with in terms of its importance or impact, then we stop where we are. Now, once we've debugged the code and the algorithm has succeeded on what looks like our original series, we switch to the real data and we find the limits of the algorithm. When does it fail? How much does it fail? And where is its weaknesses with regard to finding the curves that are there? And if that algorithm does not find the parameters or the curves as we need them, we consider other algorithms. If we look at state space approach for each technique, there are many toolboxes and algorithms for control theory that could be applicable here. Please note that exponential smoothing, double exponential smoothing, Fourier series, ARMA, ARIMA processes, and higher order models can be converted to state space, and therefore the same algorithms are used over and over again which means you have less chance of an algorithm problem or a software problem as you proceed. If we're going to fit linear combinations, we have to define those functions and determine if they are or not basis functions. They should be basis functions. We then have to formulate the overdetermined system to solve it. Remember that the data we collect will not solve exactly for the set of equations because of the errors involved. So we're going to do solution via normal equations or via QR factorization. So we're going to come up with a best fit of the data. If we have linear combinations, such as f of x equals sum of other functions, linear added, the basis functions are going to be chosen by the person making the fit. And this is where the art comes in. Which basis functions best fit the data you have? For the demand forecasting, the cosine and sine work very well. There's obviously a trend in seasonality included, but the curves, as you look at them, obviously are sinusoidal or cosinusoidal for some degrees. And all we need to do then is determine what the coefficients are for the various terms. So what basis functions could we use? Well, any of them that are linear in the coefficients. Valid basis functions include everything from a constant to x squared, sine x, e to the x, xc to the x, cosine of log natural 25x. All of these can be used as basis functions. Functions that are not valid basis functions because of the c sub j being internal, a coefficient inside of the parameter fit, are not to be used. Combinations, well, we just add all of these that we want the objective. We want the objective that finds the right coefficients such that the function we have assumed to be our data is actually equal to our data. So as we look at the residual of that fit for each of the data points, we want to minimize this. So this is where we do least squares, an absolute value solution to find those coefficients that give us the best curve fit. In terms of combination of functions, we can consider, for example, three basis functions. Let's assume we have three cosines or a linear term, a seasonal term, quarterly, and a cosine for the day. We can use all three of those as basis functions and then use the function that is a combination of those as an interpolant that basically interpolates so that we get the right combination given the C's to J's. So we want to find an interpolate that finds the best coefficients so that all of the equations are satisfied. That is, the estimated function is equal to the real data. Now, for any least squares curve fit, the equations cannot all be satisfied. There's always going to be noise, okay? Because the function cannot pass through the data. Otherwise, we would have just a set of equations and unknowns to solve. So we have to form an overdetermined system and solve for those solutions, which gets us back to the least squares matrix form, as we did with state estimation. Then we have the function we wish to fit is a matrix recursion that cannot be solved exactly. B does not lie in the column space of A, that is, the equations cannot go through all of the data points, so the least squares gives us our best solution. And here we're back at the state estimation formulation to solve those problems. Now, if we have generalized this to n basis functions, we come up with the same answer in the end, except that we're now looking at a matrix vector product. We've been writing the fitness function as a summation of other functions. The overdetermined coefficient matrix contains the basis functions evaluated at the known data points. So if A is available, f of x equals c, we can evaluate the function we are proposing with all the values of x. And so this is now a vector valued function. The advantages of a matrix vector product or a vector product solution is the basis function are defined in only one place, in the routine for evaluating the overdetermined matrix. The automation of fitting and plotting is easier because all that is needed is one routine for evaluating the basis functions. Indeed, in our case, we could reuse the state estimator code once again by rewriting what is unknown and what is known. End user of the fitness, not the person performing the fit, can still evaluate the fit function by looking at the actual data and the data that is predicted. So the end user can determine how well the forecast function fits their needs. The disadvantages is the matrix A is large, so a lot of memory would be used, not a major problem today for the small n we're looking at for forecasting. And the evaluation of the fit function may not be obvious to a reader unfamiliar with linear algebra and what kind of quality of fit is there. The Matlab implementation and the Matlab site contains several good examples of electric price forecasting, of market forecasting for trading, and a good part of that is very similar to the state estimation we've done. But what the Matlab implementation would look like for this is we have the columns of A are the basis functions that evaluate each of the X data points. Just as before, the nominal equations are solved. The user supplies a usually small M file that returns A when using the standard software for Matlab. If we compare this to state estimation, parameter estimation is the same as our estimation of transformer parameters are transmission line parameters. So instead of estimating the state, the equipment parameters are estimated instead. And indeed, this is something that we should be aware of how to do because of the origins of data for state estimation are wholly inadequate next to the values. I often compare state estimation, parameter estimation, to a resistor. We can either determine the value of a resistor by going through the components it's made of, that is the chemicals, the compounds, how it is manufactured, how is it encapsulated in the end, and come up with this resistance. Or if we really want to know the resistance, we can just take a voltmeter and measure the resistance. And that is what state estimation allows us to do. Instead of looking at a transmission line and going through all of the ground effects, the kind of soil underneath, the sag between towers, the amount of transmission line movement as the line heats up and therefore expands, etc., it's far easier to put a voltmeter across. And that is why phasor state estimation is so important and far more accurate for given conditions. So all we need to do is exchange the variables from unknown to known status and from known to unknown status and run the software once again. So parameter estimation is typically a second pass state estimation process that is needed to verify or benchmark the input data. But again, the students should be aware that we're all back at the same equations once again and the importance of knowing how to apply this to both cases. Example curve fit. One of the examples on the spreadsheets is how do we fit the input-output curve for a power plant? After all, we cannot measure exactly the tons of coal, the barrels of oil, or the cubic feet of gas going into a boiler or to a turbine, and therefore there's uncertainty in measurement. So what we have to do is we have to take samples of that data over time and some sensor to measure the input versus the output. Of course, there'll be errors in both, although the measurement of the voltage and current is far easier than the fuel going in. And we can come up with a production cost curve for the power plant as the quadratic function used throughout all of the economic dispatch presentation. It is interesting to note that the Electric Power Research Institute found that a reduced cubic worked, and this is one of the homeworks that will be assigned. Which would be better? The reduced cubic, where the square term is missing and the cube is there instead, or the original quadratic? One should note that any valve point problems will clearly show that this is a very hard problem to fit. And there'll be more discussion of that with the homework. As we do the fuel data curve fit, there will be a spreadsheet available. The data actually comes from a parabolic curve. We're going to minimize the sum of errors squared using the Excel linear programming or optimization code. And we will generate points for a fossil fuel power plant. And we will have some, of course, where the reduced cubic is a better fit. The whole idea here is, in all of forecasting, we wish to be parsimonious. Parsimonious is a nice word. It's one of those things that you'll hear time and again. And what it means is you want to use the least amount of structure and parameters to come up with a good forecast. If you can use fewer terms, fewer functions, fewer parameters, and come up with a forecast with the same error, you are ahead of the game. One of the discussions I get in with one of the hydro companies is they were using a 13th order polynomial curve fit function for hydro curves to convert the water flow, which is cubic feet per minute or cubic meters per minute, to the power output. And I was curious why a 13th order polynomial could be justified. Unfortunately, we couldn't find the original documentation. But that is another place where we must remember that we should be parsimonious, or as one of the other documents or keywords we like to use is KISS. We want to keep it simple and straightforward. We don't need to come with 14th, 15th, or 20th order anything if a second order polynomial will do the same job. It just doesn't make engineering sense. So, in summary, Excel and other optimization programs offer many examples of curve fitting. You'll find many on the internet web in terms of linear and nonlinear regression. These are all very standard optimization problems, so your experience with economic dispatch is totally appropriate here. Your knowledge of linear programming is very good here. And for those who go off to Matlab, the Matlab toolboxes are extensive to work in this area. And Python, which is one of the newer languages, offers a high number of platforms and toolboxes for higher order solutions and very easy to use. Another language that is used in this area quite extensively is R. And if you're a statistician, you know what R is and how to use it. And that's why we won't go to this course. Again, go back to the state estimation lectures that you had and the state estimation derivations and equations. And just remember that all we have to do is we're no longer estimating the state. We're estimating the parameters of the functions relating the physics of what is going on underneath. And that's one of the easiest ways to handle curve fitting. One of the techniques we have not covered is the least absolute value by linear programming, and we will leave that as a potential homework problem. And comparing those two has been done extensively in the literature.